And if there are any questions in the chat, maybe Uncle, you can read them out as well for me.
Yep. So,
Great. So as I was talking to some people, before just a few minutes ago, it seems like dark matter is a big topic these days. And this work is sort of our humble attempt at bringing the tools and technologies of quantum information to that field. So let me tell you about our work searching for dark matter with superconducting qubits. And this work was done by me, but also with many very talented graduate students, the postdoc I work with very closely, and my advisors, Aaron and Dave, and conducted at the University of Chicago. Okay, here we go. So what exactly is dark matter? I won't get too much into the details. I know this is a quantum information crowd, so I'll just give you the big picture overview here. So there's sort of lots of lines of evidence that lead us to think of the existence of dark matter. The first is sort of looking at the rotation curves of galaxies, meaning how do stars at different radius in the galaxies rotate around the center. And this is sort of consistent with galaxies being embedded in a halo of dark matter. If you look at sort of the spectra of the CMB, or the cosmic microwave background, which is the light coming to us from the earliest times in the universe, you see signatures of the presence of unknown dark matter. These spectra, and probably the most visually stunning piece of evidence, I think, for dark matter is if you just look out there into the sky, you'll see that light from distant galaxies is being bent in a manner consistent with Einstein's theories of relativity, and you infer that between you and the object you're looking at, there's a large dark mass. And I think probably the most important role that dark matter plays is, well, without the dark matter, the structure in our universe just wouldn't exist. There wouldn't be enough matter in our universe to form the interesting structures that we see, such as galaxies and stars and planets and us. So I guess as an experimentalist, my question is, well, what is the dark matter? And there are sort of a zoo of theories and hypotheses for what it could be. Everything from things like dark electrons and weakly interacting massive particles, dark neutrons, and there's probably many more that I don't even know about and are definitely not listed here. The things that I think about are a class of dark matter candidates that are very light in mass and are very weakly coupled to the universe that we interact with on a daily basis. And one of these candidates is called the axion here, and there's another candidate I'll tell you about as well. So the way we think about trying to detect the dark matter, or these candidate dark matters, is through electromagnetism. So two candidates that I'll focus on today are this thing that I mentioned before, the axion, and second, the hidden photon. And the most important thing to take away here is under the right circumstances, which you engineer in the lab, we believe that these candidates will convert into a photon whose energy, whose frequency is related to the mass of the dark matter particle, the axion or the hidden photon. So in our case, we hypothesize that the light that is produced here is sort of microwave photon, microwave energies. And you can see the mean number of photons that we think will be produced is very small, meaning the probability of conversion from dark matter to photon is extremely small. The typical way that the search for one of these particles proceeds is we build a microwave cavity, which is really just a box with shiny walls to contain photons and is the right shape to contain photons of a particular size, in this case, microwave photons. So you can see the sort of size scale of this cavity is a few centimeters, or even probably about a centimeter or two. The next thing we do is we route the signal from inside the microwave cavity to an amplifier that is operating at the quantum limit, which we hope is the lowest amount of noise we can have for this chain. Okay, so this is really nice if this is possible. There are, of course, a couple of challenges that we typically run into when we try to do these type of searches. The first is when we use one of these amplifiers, we are limited by the amount of noise that is required to be added by using one of these amplifiers. And this is usually referred to as the standard quantum limit. And that injects what's the equivalent of about 1 photon worth of noise into our measurement. And as I showed before, the signal that we're looking for is well below this mean 1 photon. And so eventually, as the signal gets smaller and smaller, the search becomes untenable. One thing I didn't mention is we don't know the mass of the dark matter. And what that means experimentally for us is that we need to tune the resonant frequency of the cavity to search over many possible masses or equivalently frequencies of the photon. The thing that we run into there is as we increase the frequency of the search or look for slightly larger and larger masses, the effective size of our cavity has to shrink to match that resonant condition. And this ends up meaning that the signal that we get potentially scales very poorly with the frequency that we're searching at. And so in this presentation, I'll tell you about our efforts to both circumvent this quantum limit imposed by using amplification, by switching to photon counting. And then time permitting, I'll tell you a little bit about our work enhancing the signal to combat that poor scaling of the frequency by using stimulated emission. Okay. So as I alluded to, the typical strategy for measuring the signal inside of one of these cavities is to use linear amplification. And what that really means is you're trying to measure both the in-phase and out-of-phase quadrature of the field inside of the cavity. So you can see here both the blue and the orange are the in and out-of-phase curves. And what Heisenberg's uncertainty principle tells you is that you can't measure both of these components of the field with arbitrary accuracy. There's some penalty you have to take, and that comes in the form of this standard quantum limit, where you have an effective added noise from this amplification technique of the equivalent of 1 photon. So what's the way to get around this? Well, don't measure both the in and out of phase quadratures of the field. Instead, just measure the amplitude of the field. And that's effectively what counting photons is, right? If you only measure the signal amplitude, what you give up is all information about the phase of the field that you're looking at. And this is what makes this consistent with Heisenberg's uncertainty principle. The thing you might ask is, well, don't you want the phase information? For determining the existence of the dark matter and the existence of a photon produced by the dark matter in our cavity, all we really care about is, was there a photon or not a photon? And giving up the phase information is something that we're willing to do in order to do this search. And effectively what this means for us is that we can measure the amplitude or one of the quadratures of the field with very high accuracy while giving up all information about, in this case, the phase. As a comment, LIGO does exactly the opposite thing, right? They measure the phase of their field really, really well while giving up all information about the amplitude of the field. And that's how they sort of measure the differential arms of an interferometer. And so a lot of our work is inspired by really good work that's come before, including people at LIGO, and of course, a lot of people in the quantum information world. Okay, so photon counters already exist in the form of these photomultiplier tubes that they use here at Superconducting, including single photon nanowire detectors, these SNSPDs, where you absorb a high frequency photon and have one of these hotspots. But the thing is that these photon counters exist for sort of terahertz high energy photons. For the microwave photons that we're looking for, we need to come up with a new way of detecting them. And so I'll spend a few slides showing you the sort of devices that we work with and why they are useful. Okay, so the basic type of device that we think about is a superconducting qubit coupled to a microwave cavity. And the Hamiltonian that describes the system is sort of spelled out here. And I'll go through each of these pieces in the next few slides. But as a basic setup, there's a microwave cavity here that I call a storage cavity. There's what I call a readout cavity, and then there's a qubit bridging both of these cavities. And we use the readout cavity, of course, to read out the state of the qubit. The idea here is that the dark matter will inject a photon into the storage cavity, and then we'll use the qubit to measure the presence of that photon. And here are some numbers for those interested. We're working at the sort of few gigahertz regime for our cavities as well as our qubit. Okay, so the first piece is making a really good microwave cavity. And this is a technique that we've sort of devised in our lab at Chicago, where we're able to make a microwave cavity sort of in this region in a seamless fashion, so without having to put two pieces together. So this is a monolithic block of aluminum that we can machine in a clever way to produce a cavity that lives sort of in the center here. And this allows us to achieve really high quality factors, which is important for us because once the photon is potentially injected into the cavity, we want it to live for as long as possible so we have enough time to measure it. And the Hamiltonian here describes the cavity. Maybe I'm going too much into detail, but it's described here by the number operator, how many photons there are in the cavity, and some characteristic energy scale, which is here we call omega c. The second piece of this is really the qubit, right? So I'll admit the thing that we're really good at making are LC oscillators, right? Most of us are very good at making harmonic resonators. And so that's exactly what we do. We basically make LC resonators, but in order to make the qubit, what we do is we add a tiny nonlinearity in the form of a Josephson junction. And this takes what's usually a quadratic potential that leads to the harmonic oscillator and turns it into a sort of sinusoidal potential. What this means effectively is that the energy levels here are no longer equally spaced as they are in a harmonic oscillator. And then you can identify sort of a subspace here at the bottom where you can call the lowest lying state the ground, and then the next excited state the excited state, and operate the system as a two-level system, which we call the qubit. The way we make these qubits is we have these dipole antennas that are sort of a way to couple to the outside world. And then if you zoom in, you can see the Josephson junction, which is really at the heart of this device. And the junction is really a layer of superconducting metal, so aluminum, and then another layer of superconducting metal, aluminum, and between them we have an insulating layer, in this case, aluminum oxide. And you can see the size scales of the metal are sort of at the 100 nanometers level, and the thickness of the aluminum oxide barrier is sort of about a nanometer. Okay, now that we have our cavity and we have our qubit, the next term here is how do you couple these two things together? In the case that we build where I put these big dipole antennas on our qubit, it's actually pretty intuitive how we couple. It's really a dipole interaction between the qubit and the electric field inside of the microwave cavity. And so the Hamiltonian of the interaction ends up looking like a D.E type term. And if you do a little bit of math and some approximations where the coupling rate is small compared to the energy difference between the two objects, you can come up with this interaction term where you have some engineerable energy scale here, 2 chi, and the product of the number operators of the cavity, A dagger A, and the qubit, sigma z. And there's some details for the experts over here on the side. And this interaction is going to be extremely useful to us, and I'll tell you about how that's useful for us. Basically, it's at the heart of all the experiments that we do. Okay. The last piece of paperwork here is that once we have our cavity, we have our qubit, and we've got them to interact, we need to take them to really, really cold temperatures. And in our case, we use a dilution refrigerator to take them down to 8 millikelvin, about. There are 2 main reasons that we need to do this. The first is we use aluminum in all our devices. And so we need to get below about a Kelvin in temperature for all of our materials to go superconducting. And probably the most important reason why we need to go to cold temperatures is, remember, we're looking for the presence of a very rarely occurring photon coming from these dark matter signals. So we don't want to get ourselves confused with thermal photons just present from the ambient conditions. And so the goal is there to go to extremely cold temperatures to make sure we don't have any thermal radiation. Okay. Any questions so far? I might take a minute pause here if people have any ideas.
Shreyas, would you like to unmute and ask your question, or? So there was one question, what is G and epsilon on the first slide? So this was, I guess, cavity and...
Get there really quickly. Yes, okay. So these G and epsilons are sort of parameters that characterize the probability of converting between the axion and the microwave photon, or the hidden photon and the microwave photon. And these are sort of the parameters that we're trying to determine, right? If they're not zero, we want to figure out what they are, right? And so these tell us if we find that there is a non-zero G or a non-zero epsilon, that is what we would use to prove the existence of either of these candidates. And it's a model parameter, right? People have hypotheses for what values these things could take. But I would say they are unknown still. And the goal of these experiments is try to figure out what they are, or at least constrain what they are not in some cases.
Okay, thank you. There is another question.
Sure.
Would you please explain quantum noise limit concept?
Yeah. So let's go back here. So really, this is just a manifestation of the Heisenberg uncertainty principle. So if you try to measure both, say, the momentum and the position of an object, you can't get below the Heisenberg uncertainty principle. You'll have noise in both of those pieces of information, right? And the reason is because position and momentum are these conjugate variables from each other. And similarly, the in-phase and out-of-phase components of the microwave field are also conjugate variables. And so if you attempt to measure both of these pieces of information, you end up with a similar situation where you have noise in both of them, equivalent to about a photon's width of noise. And again, this is really just a manifestation of the Heisenberg uncertainty principle. And yeah, there's a direct analogy between position and momentum. Typically in phase space, the x-axis would be position and the y-axis would be momentum, and you would have an incompressible spot in the phase space that represents sort of this Heisenberg uncertainty principle. And it's exactly the same for this type of situation where you have the in-phase and out-of-phase components of the field.
Perfect. Thank you. I have another question.
Sure.
Can we treat axion as a field itself, not mass? Can this field interact directly with the dipole?
That's a good question. Again, remember, the things that I'm talking about are models and hypotheses.
Mm-hmm.
If we wanted to, we could write down a hypothesis like the one you're describing. It's just for the conventional ones that people think about, the axion does not directly interact with the dipole. For the axion case, right? Because particular conditions of the axion experiment require a magnetic field. For the hidden photon, actually, people have been thinking about this question a little bit, where the dipole moment of the qubit can directly interact with the field sourced by the hidden photon, right? And so there's I don't have the reference with me right now, but there's a cool paper that came out recently, a theory proposal where you can just watch the qubit and see if it Rabi oscillates, and that tells you if it's interacting with some unknown field. So it is possible, I think.
Okay, interesting. And just to make sure, in the dipole interaction term, electric field is the secondary field which was converted from axion to the photon.
Exactly.
Okay.
This is the field. This is the photon field, essentially. This is
Okay.
the electric field. And the idea with using a cavity here is that you want to match the field of the photon that you're producing as well as you can to the nominal electric field of the mode of the cavity. And that gets you this enhancement because the field will then interfere with itself constructively and build up. And that's sort of the reason people use cavities rather than using a broadband. Remember, the signals are so small that you want to get as much gain as you possibly can. And using sort of the quality factor of the cavity is one way of doing that.
Perfect. Thank you. We can move forward.
Just a quick question.
Sure.
So regarding the SNSPDs, I didn't understand what's the exact problem. Like, what's the energy scales that you're interested in?
I'm interested in sort of gigahertz energy scales, sort of 1 to 10 gigahertz energy scales.
Okay.
And so those are still a little bit too low energy to end up sort of breaking the Cooper pairs that you need for these to get a useful signal. Although people in the SNSPD world are sort of now operating at the sort of hundreds of gigahertz frequency scales. And so it is all possible that these things will end up overlapping. It just hasn't happened yet.
Okay. Yeah, thanks.
Yeah. Okay, cool. Okay, so now that we have our device, our cavity qubit, they're interacting, we've gotten them cold and they're all working. How do we actually use the interaction that we've built to count photons? In this slide, I've suggestively rewritten the Hamiltonian where I group the interaction term with the qubit term. And what this ends up looking like is that the qubit term, the qubit transition frequency is now a function of the number of photons in the cavity, right? So anything in front of the sigma z tells you about the qubit frequency, and one of the terms in there has this A dagger A in it, which tells you about the number of photons in the cavity. And you can see that here in the experimental data where we're looking at the spectra of the qubit. So everywhere you see a peak, that's a possible place you can excite the qubit, right? So you can excite the qubit here when there's 0 photons in the cavity. But when there's 1 photon in the cavity, you can see that the qubit transition frequency has shifted by exactly this 2 chi here that we've engineered in our interaction. And similarly, if you inject 2 photons, you can even see a little bump here for the 3 photon peak. And so the question then becomes, how do you infer the state of the cavity just by measuring the qubit transition frequency? And that becomes a matter of interferometry or doing selective number pulses on here. And so I'll tell you about the exact protocol that we use. But maybe I'll just pause quickly just to make sure everybody understands this slide here, because this is sort of at the heart of what we're working on. Remember, the transition frequency of the qubit is a function of the number of photons in the cavity. And again, we'll have another pause at the end of this sort of section where we can come back to this if that's useful.
What's in the y-axis?
The y-axis tells you about the probability of exciting the qubit.
Okay. And this is the same parameter G or epsilon, I guess.
G or epsilon are not part of this plot yet. G or epsilon are the sort of dark matter to photon conversion probabilities. This just tells you if I try to excite the qubit at, say, this frequency, what is the probability that will, while this cavity state is coupled to it, right? So in this case, what I actually do is I prepare a coherent state in the cavity where the cavity has a superposition of 0, 1, 2, 3, and all the rest of the photon numbers with different weights. And then I say, can I try to excite the qubit here, or here, or here, or here? And the levels here tell you about the probability of being able to do that.
Okay.
Yep. Okay. So Knowing this, our goal then becomes measuring the frequency of the qubit, essentially, to infer then the number of photons in the cavity, right? And one of the ways in which we do that is we use what's called a parity measurement, right? Okay, so let me walk you through this really quickly. We'll take two situations, one where there are 0 photons in the cavity, and the other situation where there's 1 photon in the cavity. And both of them will start with the qubit in the ground state. This block sphere here represents the state of the qubit while I do all my operations. And pointing down means that the qubit's in the ground state, and pointing up means that the qubit's in the excited state. So the first thing I can do is I can apply pi over 2 pulse to the qubit, and this rotates it from pointing along the z-axis and puts it into this horizontal plane along the x-axis. Then I just wait, actually. And because the transition frequency is different in the case where there are 0 photons versus the case where there's 1 photon, the phase of the superposition state of the qubit will rotate at a different rate. And this is just typically what people call precession, right? This is effectively like taking a spin and putting in a magnetic field and then misaligning a little bit, and you'll see it rotate around. And so in the case where there's 0 photons, effectively the qubit does not rotate at all because its transition frequency has not changed. But when there's 1 photon in the cavity, the qubit transition frequency has shifted by exactly 2 chi. And so the phase of the superposition rotates at a rate of 2 chi. So if you wait just the right amount of time, specifically, 1 over 2 chi, you'll see that when there's 1 photon, the qubit has sort of rotated all the way to the other side of the block sphere. Now, if you apply the right pulse, you can project these 2 states back onto the z-axis, and you'll see what we've done here. When there are no photons in the cavity, the qubit state remains unchanged in this protocol. However, if there's 1 photon in the cavity, the qubit state is flipped due to this protocol. Right? You can see we started in the ground state, then rotated around, and then end up in the excited state. And so this is the signature that we'll be looking for. We'll see if the qubit flips, we'll infer that there was a photon in the cavity. If the qubit stayed in the same state, we'll know that there were no photons in the cavity. Okay. So when we first thought of this, we just went ahead and tried it out. So what we did is we prepared the cavity with no photons a bunch of times, and then we also prepared the cavity with 1 photon a bunch of times. And then we just applied this parity measurement. And you can see most of the time we get 0 when there are no photons, and we can get 1-ish when there's 1 photon. But the thing that we notice is that even when we prepared 0 photons, we see the qubit occasionally. And vice versa, when we prepared 1 photon, we see that the qubit flips down into this ground state here, telling you that there's some errors going on here. And we call these the false positives, which mean that even though there were no photons, it looks like there was a photon due to an error of our measurement. And the false negatives here are, even though there was a photon in the cavity, we missed it because of an error in our measurement. And these are the false negatives, and these lead to inefficiencies. Specifically, the thing that worries me the most are these false positives, right? I don't want to be the person who claims to have seen dark matter, but in fact was being messed up because of an error in my measurement, right? And we sort of understand why these errors occur. There's a lot of literature recently in the superconducting qubit world talking about its flip, even though we don't want them to, and the sources of these types of errors. But we do know, and we have measured, that these errors occur at the sort of few percent. And that is much higher than the probability of seeing a photon from the dark matter. And so this is sort of impossible to work with unless we figure out a way to deal with these errors. Okay, and again, the way we do it is we go back and look at the Hamiltonian that we've constructed for cavity, qubit, and the interaction between them. And we note that the interaction term is really just a product of the number operators that are here in the bare Hamiltonian of the cavity and the qubit. So it's A dagger A times sigma Z. And for those of you who've taken some graduate quantum mechanics, what this really means is that this term commutes with the rest of these terms. And so that means for effectively for us as experimenters, you can use this interaction term to measure the number of photons in the cavity without destroying that state, right? You project yourself back onto an eigenstate of the original Hamiltonian by using this interaction term. And what that means for us is that we can then just measure the same photon again and again and again using this interaction term without destroying it or absorbing it. And that's sort of a key insight here into this work. And what this means intuitively for us is that even if there are occasional errors in your measurement, the fact that you're able to make this measurement many, many times sort of reduces the chance that you'll be swamped out by these errors. And I can formalize that in the next few slides, and I'll show you a few examples of that as well. Yeah, so I guess the way I said this in my notes is that by making multiple measurements, you have insurance against individual errors in any particular measurement. Okay, so a little bit of math here. We use what's called a hidden Markov model to describe this evolution as we make multiple measurements, where the qubit and cavity are sort of moving in time as we make each of these measurements, and we're also reading out the state of the qubit. And the things that go into this model include all of the ways in which we can have errors present in our measurement. This includes decay of the qubit and cavity states, spurious heating of our qubit, so our qubit jumping from the ground state to the excited state. And it also includes things like the dephasing of the qubit. So this tells you how long the qubit stays in that superposition state before dephasing. Additionally, we include things like what is our ability to measure the state of the qubit. It's called the readout fidelity, and that's sort of at the 95% level. So after including all of these things into this model and making these many, many measurements, our goal then is to ask the question, well, what was the probability that there was a photon in the cavity after seeing this particular sequence of measurements? And so that ends up looking like this equation over here. And we call this reconstructing the cavity state. But maybe, I mean, this equation is kind of hard to parse. So we'll just go through a quick example. So say you observe the sequence of the qubit in the ground state and then the qubit in the excited state as you make multiple measurements. So just to give you a little bit of intuition, we'll talk about all of the processes that are included in this reconstruction that could lead to this type of sequence. So the first case is, well, say there was a photon in the cavity, the qubit successfully flips due to the presence of the photon, and then we correctly measure the state of the qubit. This would lead to this G to E sequence. Alternatively, there could be no photon in the cavity. The qubit is incorrectly flipped, either due to one of our pulses or due to heating of the qubit. But then we correctly measure that the qubit has now moved into the excited state. And the third option is there's no photon in the cavity. The qubit correctly stays in its original state, does not flip, but we make a misassignment or an error in our readout of the qubit. Right? This could also lead to the sequence. And so we count for all of these types of processes in this reconstruction. And from this, we're able to then assess whether or not there was a photon originally in the cavity when we first started this measurement sequence. So let's go through a couple of examples here. So on the left, I'm showing you what is the state of the qubit as we make these many measurements. And on the right, I'm showing you what is the reconstructed probability of there being a photon or not a photon in the cavity. So you can see on the left, as we make measurements, the qubit basically stays in the ground state the whole time. And what we infer from that is that with very high probability, there were no photons in the cavity. This intuitively makes sense, right? We said that if there was a photon, the qubit would flip, and we don't see any flipping happening here. Okay, so maybe the more exciting case is what happens when there is a photon in the cavity. Here you can see that when there is a photon in the cavity, the qubit state flips back and forth between the ground state, excited state, ground state, excited state, so on and so forth. And when we apply our reconstruction, we can see that as we make more and more measurements, we become more and more confident that the zero photon hypothesis is not the correct one. And with a very high probability, we can say that there was in fact one photon in the cavity when we started this measurement. And the key thing here to remember is this y-axis here is on a log scale. So we have an exponential suppression of the false positive probabilities with only a linear increase in the number of measurements we have to make. And that's a trade-off we're always going to take. Okay, so now that we have our ability to measure photons in the cavity, suppress false positives from measurement errors, the goal then is to characterize this detector. And that's what we do here. So on the horizontal axis is the injected photon probability, which we choose to be very small, commensurate with sort of the dark matter level probabilities we expect. And on the vertical axis is the probability of measuring a photon. And this really just comes from, in each particular preparation, we either count was there a photon or not a photon using our repeated measurement protocol. And that's what this probability is telling you about here. There's sort of two important parts to this plot. Up here, where we inject a higher photon probability, we can see that we measure those photons with something like a 40% efficiency. Then as we reduce the number of photons that we inject, we see that this curve flattens out. You'd expect that if this was a perfect detector, this curve would just continue to go down and down and down. Instead, it flattens out at the sort of few 10 to the -4 level. And what this tells us is that our detector has a false positive probability of a few times 10 to the -4, meaning that even if we don't inject any photons into the cavity, we still measure a population of something like a few times 10 to the -4. And one of the things that I will stress here is that this is even after we've used our repeated measurements to suppress false positives coming from measurement errors. And so we wanted to think about, well, okay, so where is this false positive? Where are these false positive events coming from? And so what we did is we went and looked at the events on a sort of case-by-case basis. And in these histograms, I'm plotting on the horizontal axis, sort of the log likelihood. So this tells you sort of in a log scale, how probable it was that the event that you saw was a photon. So the higher this number is, the more likely it is that the event that you saw was a photon. And so when we inject an appreciable photon population into the cavity, we see quite a few events here where we're pretty certain that these are real photons that we're measuring. Now, when we drop the probability of injection, we would expect there to be almost no events at all. But instead, what we see is we see a handful of events with a very high likelihood of being photons. And by high likelihood, I mean, these are events where we've suppressed the measurement errors from being the source of these, but are in fact now measuring real photons that are present in our cavity, even though we have not injected them. And accounting for the efficiency of our measurement, we conclude that our cavity is filled with a background photon population of something like 7 times 10 to the -4. And the key here I want to stress again is that we've eliminated our detector errors as the source of these events and are now in a regime where we are measuring the intrinsic photon population of the cavity, even when we did nothing. Okay, so finally coming back to the actual dark matter part of this talk, what does this now mean for our dark matter experiment? And the way I like to think about it is, for a given dark matter signal that you are trying to look for, how long do you have to measure for in order to see that? And basically, this is an argument of signal to noise, right? If your signal is large compared to your noise, you'll be able to quickly see that signal. But when you rearrange these equations, what you see is that the time that you have to integrate for, or that you have to measure for, is proportional to the background of your measurement. And in our case, the background is this few times 10 to the minus 4. If you use a linear amplifier, like I mentioned earlier, is this traditional technique of doing these experiments, you have the effective background of the quantum limit, which is 1 photon. And you can see just by doing this comparison that by switching from amplification to photon counting, you get something like 1,000 times in lower background, which means you have to measure 1,000 times less time. And this is always huge. This means a graduate student never finishing their project versus being able to finish 1,000 times faster. And again, that's a win we're always going to take. Okay, so how do you actually do a dark matter experiment with one of these qubits inside of a cavity? And the protocol goes something like this. First, you wait and let the dark matter interact with the field inside of the cavity to potentially produce a photon. And then you apply these repeated measurements, these repeated parity measurements that I mentioned. And then you do this analysis that I talked about with the reconstruction and the hidden Markov model. And you infer, okay, did I start with a photon in here, or was there no photon in here? And we did this a couple of times and we made some improvements each time. I'm mostly going to be talking about this first run, where we had this background population of 7 times 10 to the minus 4. And one of the key metrics that we think about is the duty cycle. So how long do you have to measure compared to how long is the total experiment time, right? And in this case, because we have to do 30 of these measurements, it takes a significant chunk out of our measurement time. Remember what I talked about earlier, where when we do these measurements, we're really projecting the state of the cavity. And what we in fact see is a Zeno effect on the cavity state. We can't accumulate the dark matter induced signal while we're making our measurements. And so this is really dead time. And one of the goals that we've been thinking about is how to reduce this measurement time so that we can be almost always integrating the dark matter signal. And you can see that with some improvements that we made, we went from 65% of the time integrating to 80% of the time integrating. Right? And we'd like to get this number up closer to something like 95%. And we worked a little bit on the experimental setup and reduced the background population of the cavity a little bit. Okay. So the question we then want to ask is, after we conduct these experiments, well, did we see dark matter? And if we didn't see dark matter, what dark matter parameters have we excluded, or what hypotheses have we ruled out? And that's typically the way these experiments are framed. Okay, so this may be a slightly unintelligible plot for those of you who have not seen plots like this before, but I'll walk you through it a little bit. So on the horizontal axis is the hypothetical mass of the dark matter that we're looking for. And on the top here, I've converted it into a frequency of photons that we're looking for. And on the vertical axis here is the epsilon parameter from the hidden photon, right? So our goal here is to map out which hypotheses we have constrained or eliminated, right? So every point on this plot is a potential dark matter hypothesis, where if you say pick a point here, that hypothesis that this dark matter has this particular mass with this particular coupling between hidden photons and microwave photons. And so this purple little javelin here is the range of hypotheses that we've excluded using our particular measurement. And we think because of the speed up that we've achieved by counting photons rather than measuring, we can sort of scan through this hypothesis space much more efficiently than we could if we were just using amplification techniques. And here's sort of a zoom in, and I'm happy to discuss the structure of the particular exclusion here for those who are interested. Okay, so I think I have some more time. Uncle, you should let me know if I'm running low. But I'll move on to talking about this sort of next part. But maybe I'll take a quick pause here for people to ask questions about the photon counting portion of this.
Yes, sure.
Hi, Akash. So for regarding the photon counting part, you do this at room temperature, or
No, this is all done at sort of the 8 to 10 millikelvin inside of our
okay?
refrigerator. Yeah.
And for this, do you think the dark counts is also a limitation or a problem for you?
Absolutely, right? The dark up until this experiment, our main problem was sort of our inability to control the state of the qubit and our detector errors, the qubit sometimes jumping from the ground to excited state or back and forth. And that sort of was at the sort of few percent level. Once we figured out how to do these repeated measurements, we are no longer limited by those types of errors, but are now completely limited by the background that we measure inside of the cavity. And so our ability to measure the dark matter is now completely tied to how low we can get the background inside of our cavity. Because remember, background photons look exactly like photons coming from the dark matter. They're just photons. And so if we can't eliminate the backgrounds, then we cannot see signals smaller than the backgrounds, essentially. And so I think I have a slide later on talking about what we think these backgrounds are and sort of mitigation strategies that we've been thinking about. But yes, you're absolutely right. The background is our limiting process here.
Thank you.
Yeah. Okay, if anybody else?
There are two questions on chat. So is this Hamiltonian similar to the quantum optics JC Hamiltonian?
It is the James Cummings Hamiltonian. It is exactly that Hamiltonian. And so I didn't mention it by name just in case people were confused by that. But thank you for pointing that out and recognizing that. This is exactly that Hamiltonian.
The next question we have, how can we sure it's not just some random noise that is causing a change in the qubit's state?
That's right. So that's sort of the crux of what we've been thinking about. We do know that different processes affect the qubit state, right? We understand why the qubit flips up and down, and at sort of the few percent level. And the point of doing the repeated measurements is that if that sort of event, say some random noise affecting the qubit state, occurs, that sort of happens on an individual measurement level, right? And so by repeating the measurement many, many times, we sort of become immune to a particular error that happened in any one of the measurements. And if you do enough measurements, then you can sort of beat down the chance that you will be confused by one of these measurement errors rather than by a real photon inside of your cavity. And that was sort of one of the keys that I was trying to describe here, where you can see, say, in this eighth or ninth measurement, that there was in fact an error that occurred, right? Rather than flipping from ground to excited, blah, 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 it just stayed between ground and ground. So the qubit didn't actually flip in these two measurements. And so this could occur for various reasons. Maybe the qubit flipped and then it decayed back down before we were able to measure it. Or we messed up in the readout of the state of the qubit, right? In fact, it was in the excited state, but we accidentally read it as ground. So there are lots of possible reasons why this could happen. And when we go and look at the inference we make from this, we can see that as the qubit is flipping back and forth, we become more and more confident that the zero photon hypothesis is wrong. But once we make this measurement, you see a little plateauing here, right? We become a little bit uncertain. We don't continue to increase. But then as we continue to make these measurements, the qubit continues to flip back and forth, and we again gain confidence in the ability to rule out the zero photon hypothesis. And sort of the key scaling to understand here is that we only increase the number of measurements linearly, but get sort of this exponential decrease or separation between these two hypotheses as we make more and more measurements. And so yes, dealing with qubit state changes is very important. And by making more and more of these measurements, we can sort of become immune to those processes at a certain level, right? At a level of 10 to the minus 15 or 18 or something like that. If the rate of those measurements increases, again, the slope of this curve will decrease as well, and we'll have to make more and more and more measurements to be just as confident in our hypothesis. Okay, so with that, maybe I'll move on to sort of the next piece of this puzzle. So as I mentioned, sort of in the beginning, the two main problems we face are, well, there's the noise from the standard measurement technique of amplification, but also as we sort of scan through different masses or photon frequencies, we see that there's this decrease in the potential signal that we can collect just because our cavities have to shrink to match the resonant condition. And so one of the things that we've been thinking about is there a way we can sort of enhance the signal to try to combat this shrinking of the signal from the cavity size? So let's do a little bit of math. Hopefully this is something people have gotten a chance to think about before, but I'll sort of walk you through it. The idea here is to induce an enhancement in the signal by stimulated emission. And what this means, particularly for us, is rather than starting in the ground state of the cavity with 0 photons, instead you start with, say, n photons in the cavity. This is your initial state. Then the dark matter converting to a photon effectively looks like a displacement of your cavity state. It looks like basically a push on your cavity state. The goal then is to see what is the probability that you ended up with one more photon in your cavity, right? And this works if you sort of go back down to n equals 0, right? That's exactly what we've been talking about this whole time. You start with no photons, the dark matter interacts, and then you look for the presence of one photon, right? And then you can scale this up to n, starting with n photons and looking for n plus 1 photons in the cavity. So if you go through the math a little bit, what you see is that for very small displacements or for very small dark matter signals, what you get is that the probability that you end up in the n plus 1th state when starting in the nth state is now not just the probability that the dark matter deposited a photon, but that times n plus 1. So you get this n plus 1 enhancement by starting in a higher Fock state. And this is really just the math of stimulated emission, right? You basically have more places to scatter, right? And so you have this enhancement, which you can use to your advantage now to have a larger probability of seeing dark matter induced transition to the n plus 1th state. So maybe I'll spend a few slides telling you how we actually prepare these n cavity states. And again, like everything in this talk, it goes back to the Hamiltonian that we have, right? This interaction that we have between the qubit and cavity allows you to do really fancy things like optimal control pulses, where you can drive both the cavity and the qubit, and due to this interaction, you can prepare the qubit and the cavity in very interesting states that you wouldn't be able to without this interaction. And so we sort of input all the Hamiltonian parameters that we measure experimentally into our control programs, and we are able to generate pulses that we should play for both our qubit and our cavity. And then we just do this, and then we can track what is the state of the cavity as a function of time during this pulse. And you can see that the cavity state, where this is measured in number of photons in the cavity, sort of goes up, but sort of delocalizes, and then sort of has this interesting pattern, but eventually ends up in here, the n equals to 3 state. And the reason this is interesting is without the qubit and the interaction present, it would be impossible to prepare your cavity in an n equals to 3 state, right? That is a very non-classical state that you couldn't get just by driving the cavity with a coherent tone, basically a cable and a pulse. And only due to the presence of this nonlinearity from the qubit and the interaction it has with the cavity can we prepare these interesting states in the cavity. Okay, and so our goal was, well, let's not just make n equals 0 or 1. Let's make a bunch of different Fock states, and that's exactly what we do here. So we use our optimal control drives to prepare the cavity in various Fock states, and by Fock states I mean just different numbers of photons, and exactly that photon number. So not 0 and 1 and 2, but exactly 0 or exactly 1 or exactly 2 photons in the cavity. And on the left here, I'm showing the spectrum of the qubit when we do this. And remember, the spectrum of the qubit allows you to infer the number of photons in the cavity, depending on where that sort of peak is in the transition frequency. And you can see sort of when there's 0 photons in the cavity where the qubit is versus, say, when there are 4 photons in the cavity where the qubit is. And you can see this nice trend here. We also perform tomography on the cavity state just to make sure that indeed we are preparing Fock states and we aren't missing contributions from higher numbers or seeing interesting superpositions that we didn't want to actually prepare. And you sort of see the telltale signs of preparing Fock states because you see these fringes in the Wigner tomography of the cavity state that tell you, yes, indeed, you are seeing these Fock states. And the intuitive reason I like looking at these Wigner tomography plots is that you can kind of already understand why it is useful to prepare this higher and higher Fock state number. You can see as I increase the number of photons in the cavity, the sort of spacing between these rings is shrinking and shrinking and shrinking. And so any amplitude displacement that you get from the dark matter is more easily sensed as a change in where you are in this fringe pattern, essentially, right? And that's sort of the way I like to think about why it's useful to prepare one of these high-end Fock states. But again, the math is pretty clear. The higher the number of photons that you start with, the larger the enhancement into the n+1 state. Okay, and so here's some initial results that we've been working on, where, again, this is a very similar plot to what I showed earlier, where on the horizontal axis, this is the injected photon probability, and on the vertical axis is the measured photon probability. And you can see as we increase the initial cavity photon number that we start with, these slopes are different, indicating that, yes, if you start with more photons, you get a larger enhanced signal. So you can see that even when we inject 1.5 times 10 to the minus 2 photon probability, you can actually get something larger than that if you start with, say, an n equals to in this case, the 3 photon number. Actually, this is n equals to 4. Sorry about that. And so this leads to something like a 4 dB signal enhancement. I did mention it for the photon counting, but by going from photon counting away from linear amplification, you get something like a 16 dB enhancement of your experiment. Okay, so what happens next, right? So we've both thought about how to reduce the noise that is present in our experiment, but also enhance the signal that we're looking for using these quantum techniques. And I think that's actually been really exciting for me, being able to apply these quantum techniques to these experiments. So I'll quickly go through what happens next. Here's a picture of a device that I built that I had a fun idea with, where I've talked a lot about measuring the state of the cavity multiple times. And what that really means in my mind is in time you are measuring the state of the cavity. But because the interaction between the cavity and the qubit is so useful, I think you could also measure the photon state in the cavity in space. So basically use multiple qubits to measure the same photon in the cavity. Anyway, that's one of these devices. It's one of my fun ideas that we've been playing around with. But a little bit more concretely, as I alluded to earlier, there are a lot of reasons why we think backgrounds exist in our cavity, and we have lots of ways we think we can mitigate them. I won't go into all the details, but there are a lot of references here, people thinking about these exact things in the context of quantum information. Pretty much the main ideas are, well, you have all of these control lines that come into your fridge from the outside world, and they are just not well filtered, or they are not well thermalized. And so we need to work on those. Probably the more interesting one that people are starting to recognize is that actually radiation, both terrestrial radiation by using components that are slightly radioactive, as well as cosmogenic radiation, so things like cosmic rays coming and hitting your devices, these can lead to sort of these qubit excitations from the ground to excited, the spurious noise that we see. And there's sort of lots of potential avenues which you could take to mitigate the effect of these types of events. Of course, the eventual solution is probably to go underground, like a lot of dark matter experiments, where you put your devices way underground, away from the effects of these types of radiation. And you can even get into crazy things like sourcing your copper from sunken Spanish ships from the 1700s that have never seen the effects of the nuclear bombs that have gone off on Earth, to reduce the amount of radiation in your system. And there are probably lots more ideas for why we have all of these errors and on these backgrounds. And I'm happy to discuss these ideas with lots of people, because it's still an open problem. I'm pretty optimistic just by doing a few things, we can sort of go from the sort of 1,000 times speed up that we've been seeing up to sort of like 100,000 times speed up. And so again, this is a hypothesis. I don't think this has not been measured. I think this is a possibility and something we should aim for. Last thing I'll mention is some of my colleagues are working on this project where one thing I haven't talked about at all in this work is I've mentioned we want to tune the frequency of the cavity in order to look for different mass dark matter hypotheses. And tuning a cavity frequency is a challenging problem. The typical way of tuning the cavities is by basically sticking a rod inside of them and moving the rod around and mechanically tuning the frequency of the cavity, just by changing the boundary conditions inside. We've been trying to do something slightly differently, using the tools that we have from the superconducting qubit world, where we basically take one of these tunable resonators, again, made with Josephson junctions, and we sort of move it in and out of resonance with the cavity. And this sort of creates this avoided crossing where you can move this cavity's frequency by sort of 10% level. And of course, tuning electronically is much simpler than tuning mechanically, because you don't actually have to physically move a rod inside of a cavity. And so this is some work that people are doing right now in Chicago. And I hope to tell people about it soon. And so with that, I think I will finish up. Like I mentioned, this has been a really fun experiment for me, thinking about ways in which to apply quantum information techniques to dark matter and cosmology experiments. And we sort of attacked the problems from two different sides, one by counting photons to achieve this metrological gain, but also enhancing the signal that we want from the dark matter